Hello student, welcome to the web optics course. Today we have lecture number 50, and in today's lecture we are going to continue the understanding of Fresnel diffraction for an rectangular aperture. So today we have lecture number 50. And in this lecture we are going to continue the understanding of Fresnel's integral. So let me write down what we have done so far in the last class. So by definition, Fresnel's integrals are like this: C of nu is equal to 0 to nu cos of pi by 2 x square dx, and S nu is 0 to nu sin pi by 2 x square dx. By definition, that is the thing. Then we find few more stuff, that is C of minus nu was minus of C nu, S of minus nu was minus of S nu, that is another. And then we managed to get the limit out of that, and limit nu tends to infinity, C of nu is half, and limit nu tends to infinity, S of nu is also half. Not only that, we also have C of 0 is 0, and nu S of 0 is 0. So these are the properties we try to evaluate in the last class, and we evaluate that. And now we are going to do one thing today, and that is to plot this function. So this is called the parametric representation of this Fresnel's integral, and we get a specific kind of structure which we will call the Cornu spiral. So this is parametric representation representation. In this parametric representation, what we do, that we plot the C nu and S nu in x and y axis for different values of nu. We just increase the value of nu, and then we find what is the value of C and S. And if we plot that, we get a curve like this, interesting looking curve. This kind of curve we get, and this is called the Cornu spiral. Cornu spiral. This is called the Cornu spiral. So, this is the way this function will going to behave. Now, after having the knowledge of these function from the last one day we are trying to from the last class we try to understand this. Now, we are in a position to understand what happened for a rectangular aperture, what should be the case for a rectangular aperture. So, let us frame this problem in this way. So, it is original problem that we aim for. X axis, y axis, and here we have this rectangular aperture. Like this. This is the origin. Then we have a small strip here with a width, suppose this is a width W, and this is over a height h, small h, and somewhere here we are having the source and here the point P over the axis, and from here to here I have a source here. So, let me draw the source S, and here the point P, and we draw the R here. This is R, from here to here, this is say R1 because another R is there, this is R2, this is P from S to this point O, if I write is at O, and this is Q, O to P, this is Q. So, that is the structure we are having. So, the equivalent structure I can have is this. So, the wavefront will hit this aperture, and S is here, P is here, this is P, this is S. Wavefront will going to hit this. So, from here to here we have R1, and from here to here we have R2 say, and this is the height, which is H, this is P, this point is O. So, from here to here this is P, and from here to here this is Q. Now, the field at point P due to this entire system that we already calculated for this EP, that is this proportionality, famous proportionality constant that we calculated. The intensity, the electric field at the source point S, integral over whatever the aperture we have, then if theta, that is the obliquity factor, then e to the power of I, then it should be R1 plus R2 k minus omega t, and divided by R1 R2 dA. That is the form of Fresnel's expression through which you can get this. Now, few things we are going to do here. First, we neglect this obliquity factor f theta. So, that is f theta we will consider as 1. That means f theta is equal to 1. Second thing that we do is, R1 square is essentially p square plus h square. So, that is equivalent to p square into 1 plus h square divided by 2 of p square. Now, h is much less than p. Under that condition, I can write R1 to be p plus h square divided by 2p. Similarly, R2 will be q plus h square divided by 2q. So, that is the condition when H by P is very less than 1 and H by Q is also having this condition. That simplification we have. Now, after doing that, I can write R1 plus R2 is essentially P plus Q plus H square by 2, then 1 by P plus 1 by Q. So, that is my R1 plus R2 with this approximation. We make few approximations here to make life simple, and those are the approximation we took. Now, let us rename few parameters, like let D as P plus Q, and 1 by L as 1 by P plus 1 by Q. That term was there. So, essentially R1 plus R2, will be D plus H square divided by 2 of L, and R1 R2 this is P plus H square divided by 2P multiplied by Q plus H square divided by 2Q. So, that is nearly equal to PQ, neglecting the higher order term of H, which is small. Okay. So, this is now, after having that, the EP in this notation will be this. This is minus of I K divided by 2 pi, that proportionality constant we figured out. Then there should be intensity at the source point S, the field at the source point S. Then I have integral over this factor. So, e to the power of I K, then we have this quantity. So, I can simply write D plus H square divided by 2L minus I of omega t, that is the time part. Anyway, it will nothing to do with the integral, so it will come out. Then PQ over the area, whatever the area. So, I did not put so far the condition of rectangular aperture. So, we are just general thing we are doing. So, I can write this all together, writing everything, say I K 2 pi multiplied by E S divided by P Q, put everything outside, and I write it as total field E T. Then also I take few terms outside which is not related to this dA, like I K D minus omega t. So, that is the term I take outside, and in the integral only term that is there is e to the power of I k then h square divided by 2l dA. So, E t, as I mentioned, E t contain all these terms minus I k divided by 2 pi, then E s divided by p q. Okay, these things we consider as E t. Now, let us go back to the structure, because I need to do this integral. Here we only required the structure, and the structure is like this. So, we have a rectangular kind of aperture. So, suppose this is my aperture, and this aperture, this is x axis, this is y, and we have a small segment here, if you remember. And that segment, better I said it, is distance h, and this was w. These things is dh. After having this geometry, we can write that dA, small area here, which is w into dh. So, integral will be over h. Now, let me go back to the expression of the EP. EP was ET e to the power of I k d minus omega t, that term was there, and inside the integral, now I need to do this integral over h. So, I can write h1 to h2, then I write e to the power of I k h square by 2l, then dA is w dh. That is the integral we finally get. Now, I can manipulate few things here. I can do few stuffs. For example, here k h square divided by 2l, I write it as 2 pi divided by lambda, which is the value of the k, then h square I write, and I put 2l here. So, this essentially give me an interesting thing, and that is pi h square divided by lambda l. Same thing I write in a different way. Now, let h square is equal to something, I write y square lambda l divided by 2 that I replace. Why I replace this specific term, one can understand easily. Then that gives me h is equal to y root over of lambda L by 2. So, 2h from here I write 2h dh is equal to 2y lambda L by 2 dy, or dh is essentially y by 2h lambda L dy, which is y divided by 2 of y, because now h I replace from this value, then I have root over of 2, then root over of lambda L, and then we have 1 lambda L here with dy. So, from here I can get my dh is equal to root over of lambda L by 2 dy. That I get. Now, I am going to replace everything here, and we see a very interesting looking term, and that is, if that is the case, then my EP will be ET e to the power of I k d minus omega t, and then we have W outside, then this term root over of lambda L by 2 also outside, and the integral will be some y1 to y2 e to the power of I pi by 2 y square dy. Now, essentially we have the here in this integral we have the Fresnel's integral. So, EP I write this entire thing as AP, another at the amplitude multiplying ET multiplying W, all these things, and I write AP by putting all the term inside the AP, then e to the power of I whatever is there kd minus omega t, and then I write y1 to y2 cos of pi by 2 y square dy plus I y1 y2 sine of pi by 2 y square dy. So, this limit y1 to y2 cos cos of pi by 2 y square dy can be written as y1 to 0 plus 0 to y1 this. So, after having this stuff, I can change it, and that thing will be if I change this, so it will be 0 to y1 and cos of pi by 2 y square dy plus, so here it is 0 to y2, I guess 0 to y2 pi by 2 y square dy. So, essentially this is C of y1 with a minus sign plus C of y2. So, we are almost there, So, after having this is same for sine also. So, for rectangular aperture, the field that I get EP is finally this AP e to the power of I kd minus omega t, and then we have C of y2 minus C of y1 plus I S of y2 minus S of y1. So, if that is the field, the intensity at point P, intensity IP will be mod of, it is proportional to mod of EP square, then I can write IP is I0. So, when I take mod of this square, then exponential term will go away, and essentially what we have is this. C of y2 minus C of y1 square of that plus S of y2 minus S of y1 square of that, bracket close. So, we finally figure out, so we do not have much time to discuss more about this. In the next class we will exploit this and try to understand few more stuff what happened for this aperture. So, what we get is the intensity distribution for this aperture, whatever the aperture we have, say this is the aperture. So, the intensity distribution here is related to this expression, and that expression suggests that the intensity distribution is related to this integral value, which is called the Fresnel's integral. So, in the Fresnel's integral we know that we have C1, C and S function, and we have a qualitative idea how this function behave. And in the next class we show, not today because today my time is up, that using this general expression what should be the intensity pattern for a rectangular aperture or a side one side one edge system. In a sharp edge, how the diffraction pattern will look like. It is not simple because it deals with this function Cy, C and S function, and also here the concept of Carnot spiral will come into the picture, because here you can see this is coming like Cy minus Cy2 minus Cy1 whole square and Sy2 minus S1 whole square. So, if I put y1 to be 0, then it should be simply Cy2 and Sy2 square of that. So, that is exactly in the Carnot spiral, these two parameters are there. So, with that note I would like to conclude in today's class. In the next class we start from here and try to understand more that how the diffraction pattern depends on this function called the Fresnel's integral. With that note, thank you very much and see you in the next class.